Hello everyone. Today I will give a presentation about our work, an efficient subband linear prediction for RPC9-based neural synthesis. This work is published on the Interspeech 2020. Here is the presentation video. At first, I will give the introduction of the background knowledge of neurocoder. Then, I will introduce the proposed subband RPC9 neurocoder. After that, I will show the experimental results. Finally, we draw the conclusion of this work. Let's start from the introduction. Neurocoder is a module of the modern text-to-speech system to generate high-quality speech waveform conditioned on the acoustic features. The typical neurocoders are WaveNet, WaveRN, WaveGlow, and MailGAN. Recently, signal processing techniques are introduced in the neurocoder, such as linear prediction analysis and subband decomposition. By introducing linear prediction analysis, RPC9 neurocoder can synthesize high-quality speech in a small footprint model. In addition, the subband neurocoders are also proposed to improve the synthesis efficiency. However, most of these works take the independence of each subband as a default assumption. In this paper, we introduce subband linear prediction in RPC9 for producing high-quality speech more efficiently with consideration of subband correlation. RPC9 neurocoder and its variants have shown the ability to synthesize high-quality speech in small footprint by exploiting domain knowledge in speech. It is a variant of the WaveRN neurocoder and can get natural speech with smaller model and higher efficiency. By introducing linear prediction analysis, RPC9 reduces the computational costs and shows the prospect of integrating the signal processing into the neurocoder. The main advantages of performing speech generation in the subband domain are: first, the analysis and synthesis filter banks are designed to satisfy the perfect reconstruction condition, which means the transfer error never exists in this framework. Second, the length of each subband is much shorter than fullband speech by downsampling, which reduces the complexity and improves the efficiency. Third, each subband signal represents a narrow frequency band component. We can design the neurocoder structure according to the property of each subband and do manipulation. Let me introduce the next section, the proposed subband RPC9. First, I will introduce the subband-based autoregressive model. Then, two modules of the subband RPC9, signal processing module and neural network module, will be introduced later. Like the autoregressive model in time domain, the autoregressive model in subband domain is given as follows. The probability of subband sequence can be decomposed into the product of the probability of subband samples. In previous work, each subband is supposed to be independent, so that the subband samples at the same time step can be generated simultaneously. However, subband samples are highly correlated with each other. The independence assumption will lead to the mismatch between training and inference, which makes a noise on the edge of each subband and affects the final output speech quality. In this paper, we propose an assumption: the subband sequence is conditioned on the lower frequency band. By introducing such an assumption, the joint distribution of subband samples can be decomposed into the product of each subband distribution, so that the subband samples at the same time step can be generated simultaneously without a mismatch between training and inference. The dependence of subband samples is shown in the probabilistic graph. The green nodes are independent given the blue nodes. We can generate the full subband sequence autoregressively in this order. More details are listed in our paper. Based on the subband autoregressive model, we propose the subband RPC9. The subband RPC9 consists of two modules, the signal processing module and the neural network module. The signal processing module can reduce the complexity of neurocoder by signal processing and the neural network module learns the subband distribution conditioned on the acoustic features. The following figure shows the block diagram of the analysis and synthesis stage. Firstly, the BFCC, log F0, and pitch correlation are extracted from the full-band speech as acoustic features. In the training stage, the speech is decomposed into 4 equal bandwise subbands in linear frequency through the analysis filter banks. The subband sequences are rearranged according to the subband autoregressive model. Then, linear prediction analysis is leveraged to extract the linear spectral pair features and the excitation signals in the first subband. In synthesis, the subband distribution is predicted by the neural module conditioned on the acoustic features. After autoregressive sampling, the first subband excitation and other subband samples are generated. Then, the first subband samples are generated by passing the excitation signal through the linear prediction synthesis filter. Finally, the full-band speech is synthesized through the synthesis filter banks. The neural network module consists of 2 neural networks at 2 rates, the frame rate and the sample rate. The frame rate network processes the acoustic features as condition and upsamples them to the sample rate network. 3 fully connected layers transform the context vector as the input of 3 recurrent units in sample rate network. We expect these 3 conditions will focus on different necessary information to model corresponding subbands. The sample rate network takes the 3 conditions and models the distribution of all subband samples. A gated recurrent unit named GRUA is shared by 4 subbands. After GRUA, 2 smaller recurrent units named GRUB and GRUC learn the distribution of the first subband and the other 3 subbands. GRUB takes the excitation sample at previous time step as an additional condition. The motivation of the design is that the first subband contributes more to the phase consistency and formant shape than other 3 subbands, based upon the human auditory perception sensitivity of the baseband. So we pay more attention to the first subband quality and allocate more computational resources to it. To further improve the precision, logistic mixture density network is utilized to learn the distribution of the excitation signal in the first subband. We also give a loss weighting between the negative log likelihood in the first band and the cross entropy in other 3 bands. Now come to the section of experimental results. Firstly, let me introduce the dataset. The experiments are performed on a database which consists of over 11,000 sentences for approximately 12 hours recordings by a professional US female speaker. We choose 10,500 and 500 utterances as training, validation, and test sets respectively. The speech signals are sampled at 24 kHz with 16-bit linear PCM. The acoustic features include the BFCC, log scale F0, pitch correlation, and RSP coefficients. The original full-band RPC9 vocoder is chosen to compare with the proposed neural vocoder. Besides, a neural vocoder with the same structure as the proposed vocoder is also included in the experiment as a comparison. The only difference is that the subband RPC9 vocoder leverages the proposed subband-based generative model, and the other one still takes the independent assumption among all the subbands. All test samples of synthesized speech are generated through the analysis by synthesis process. You can listen the samples from the slides or the given links.
Meanwhile, the Florida delegation sprang into action. 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 I'm trying to balance out all the emo I keep finding lately. I'm trying to balance out all the emo I keep finding lately. I'm trying to balance out all the emo I keep finding lately. I'm trying to balance out all the emo I keep finding lately. Lee, forever young and sneering, never got that chance. Lee, forever young and sneering, never got that chance. Lee, forever young and sneering, never got that chance. Lee, forever young and sneering, never got that chance. He launched his campaign for the presidency last November. He launched his campaign for the presidency last November. He launched his campaign for the presidency last November. He launched his campaign for the presidency last November.
Here are the test results. In objective test, we use the log spectral distance and Mel-Cepstrom distortion. In subjective test, Morse test is adopted on 200 cases. 20 native speakers will listen and give a score per case from 1 to 5 points. In the table, the neurocoder with the independent assumption is slightly worse than the one with the proposed sideband LPC9, which is consistent with the objective evaluation results. These experimental results could be attributed to the sideband decomposition and the well-designed structure, which decomposes the full-band speech into several sidebands with much shorter sequence lengths and reduces the modeling complexity. We also give the computational cost of the proposed neurocoder. The following table shows the cost of the neurocoders measured by G-flops, which means the float operation to synthesize 1 second speech. The proposed sideband LPC9 is 1/3 of the original LPC9 at 24 kHz sampling rate. Finally, we draw the conclusion. In this paper, we propose the sideband LPC9, a highly efficient neurocoder with sideband-based linear prediction for speech synthesis. The computational complexity is significantly reduced by exploiting domain knowledge of speech signals in multi-rate signal processing, linear prediction analysis, and human auditory perception in different frequency bands. In the tests, both objective and subjective experiments show that the proposed sideband LPC9 vocoder with the sideband autoregressive model outperforms the original full-band LPC9 vocoder while accelerating the inference speech at a rate nearly 3 times faster. Thanks for your listening.